if you have something like 1.5 dimensional space, in some sense, it's more than a one-dimensional space. It's more than a line. So that thing was so detailed. It was, you know, you can start from something. You can look at a curve, which is kind of broken, like that snowflake. And in that shape, if you keep on focusing on each part, again, you would see more kind of broken things. And in some sense, when you start with a less than 2 dimension, when you start with a line is something 1 dimension, right? And you can compute its length from here to there, right? Now, that snowflake, the fractal which it talked about, there's a way to construct that. So first you can start with a segment, okay? And then choose 2 points. Okay, and then you can choose 2 points here and here, okay? And make a triangle out of it. It would look like this. The length of what we get is more than length of what we started with, right? So if the length of what we started with was 1, if this thing has length 1, this thing has length 4/3, right? Now, we can continue doing that. We can continue to construct rectangles here, here, and here, and here, like this. We would get something of this form. Right? The length is more than 4/3. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, and 10, 11. I think it's 16/12 or something like that. And we can keep on doing that. We can keep on doing that. So the length is becoming larger and larger. And every time you do that, it becomes larger and larger. And if you really look very carefully, you would feel it has really a little more than 1 dimension. It's more than just a line. And that's really true. It's really more than 1 dimension, but the area is still 0. So it's still not 2-dimensional. There is a rigorous mathematical way to, like, based on what really dimension mean in math, really show these things are not 1-dimensional. Their dimension is more than 1. At some point, we might discuss it a little bit more, but yeah, maybe not this point. Let me look at the question. If Sierpinski's triangle is a shape with an area, how come it is left? No, it means only the boundary of the triangle. It doesn't mean the area of inside. It means that it doesn't contain this area inside. It just means the boundary around it. The triangle is made out of these sides. Yeah. Okay, so let's continue with our multivariable calculus. Okay, so we talked about vectors. We talked about length of a vector. We talked about slope of a vector. We talked about addition, subtraction, and multiplication, scalar multiplication. And we talked about unit vectors in direction of another vector, right? These are things we talk. Now, let's introduce a few more notations. So here we are in R2. This plane, we show it with R2. Why? Because here, this line is a real line, right? A line of real numbers. It contains all positive and negative numbers. We show it with R. Here we have another real line. And because we have 2 of them, it makes a 2-dimensional space, which we show it with R2. Now, there are two, as I mentioned earlier, independent directions. The x direction, x-axis, and the y direction, y-axis. Okay, this vector, the coordinates of this vector are 1 and 0. The coordinates of this vector are 0 and 1, right? Let me use another color. And these are unit vectors, right? Their length is obviously 1. This vector 1 and 0, this red vector, it has a name. We show it with I. This I is not, if you are familiar with complex numbers, it doesn't have anything to do with that number. So don't confuse it with complex numbers. It's just, they have just the same notation. They're completely different things. And this other one, we showed with J, 0 and 1. So I show this vector with I show this other vector with J, right? Now we can use these two letters to present any vector in the plane. So say we have a vector V equal to 5 and 3. Okay, I can write any vector like this, 5 and 3. I can write it as 5 and 0 plus 0 and 3. Does this thing make sense? Because if I add them again, what would I get? I would get 5 and 3, because I should add first coordinate to first coordinate, which is 5 plus 0, which is 5. And then I should add second coordinate to second coordinate, which is 0 plus 3, which is 3. So 5 and 3 is equal to 5 and 0 plus 0 and 3. Okay? Now, 5 and 0 is actually equal to 5 times 1 and 0. Why? Because if I multiply 5 by this vector 1 and 0, I should multiply 5 by the first coordinate, which is 1. 5 times 1 would be 5. And then I should multiply 5 by the second coordinate, which is 0. 5 times 0 is 0. Okay, plus. Now this 0 and 3 is actually equal to 3 times 0 and 1. Again, for the same reason. If I multiply 3 by 0, I would get 0. If I multiply 3 by 1, I would get 3. Therefore, 0 and 3 is equal to 3 times 0 and 1. Now, look at this. I show the vector 1 and 0 with I. So rather than 1 and 0, I can write I. So I would get 5 times I plus 3 times, well, rather than 0 and 1, I can write J. 3 times J. Well, to sum up, 5 and 3 is equal to 5 times I plus 3 times J. Okay? Again, since we are in two-dimensional space, we use two numbers to present any vector. Just as another example, if I have a vector which its coordinates are 4 and 2, I can write 4 and 2 as 4 and 0 plus 0 and 2. Because if I add the first components, I would get 4 plus 0, which is 4. If I add the second components, I would add 0 to 2, which I get 2. And then 4 and 0 is equal to 4 times 1 and 0. Because 4 times 1 is 4, 4 times 0 is 0. And then 0 and 2 is equal to 2 times 0 and 1. Because 2 times 0 is 0, 2 times 1 is 1. So 1 and 0 is I. It would be 4 times I plus 2 times 0 and 1 is J, 2 times J. So 4 and 2 is equal to 4I plus 2J. Okay, let me see the question. Is there notation to show that I or J is a vector, not just a variable? It is a vector. I mean, it's just a notation, but here I is a vector. By I mean this vector. They are not variable, they're just vectors. I'm using I and J, but they're really vectors. Sometimes people, like, they put small vectors about I and J to kind of remind you that I and J are vectors. Sometimes they don't. It doesn't matter. You can put vectors here. So I and J are really vectors. They're just names for these two vectors. Okay. And you can use this to do computations. So, well, if we have 4 and 2, and that's one vector, and if we have -2 and 3, that's another vector. V plus U is, we should first look at the first components. 4 plus -2 is 2. And then we should look at the second components. 2 plus 3 is 5. That's one way to do it. The other way is to say V is 4 and 2. 4 and 2 is equal to 4, 0 plus 0, 2. And 4, 0 is 4 times 1 and 0 plus 2 times 0 and 1. Therefore, it is 4 times I plus 2 times J. Well, in a similar way, U is equal to -2I plus 3 times J, right? So V plus U is 4 times I, 4I plus 2J minus 2I plus 3J. Now I have 4I here, I have -2I here. I have 2J here, I have 3J here. So 4I minus 2I, 4 minus 2 is 2, I would get 2I. 2 plus 3 is 5, I would get 5J. And the final results are the same. You see here I got V plus U is 2 and 5. Here also I get the sum is 2I plus 5J. So we get the same answer if we use this IJ notation. Sometimes they are useful. I know now they might not look very useful to you, but sometimes they are useful. Okay. Any question here? Okay. So, okay, let's continue. Okay, so if we have a vector U, which is a unit vector, suppose U is a unit vector. What does it mean? It means if we compute the length of U, I guess you used to say magnitude. The more mathematical word is length. The length is 1. So U would be something like this. This is U. It has some direction and its length is 1, right? I can look at the angle it makes with the x direction, with the x-axis, with a positive direction of x-axis. It makes some angle. Let's show it with theta, okay? The point is that in that case, U has a very special kind of presentation. U will be equal to cosine of theta. Well, if I want to show its coordinates, I can say cosine of theta and sine of theta. So for example, let's say here theta is pi over 6. Let's say we have a vector with unit length, the length is 1, and we measure this angle and we see theta is pi over 6. Pi over 6 is the same as 30 degrees. We prefer to say pi over 6 for many reasons. Using gradient, using pi over 6 is a lot better and more efficient than using degrees. So if you are used to using, if you got used to using degrees, it's better to try to use radians. It's better to say pi over 6 rather than 30 degrees. So if I want to write down the coordinates of u, it would be cosine of pi over 6 and sine of pi over 6. Okay. What is cosine of pi over 6? Does anyone remember? Yes. Radical 3 over 2, and its sine is 1 over 2. It's very good. You know, trigonometry is not crucial for this course, but it would be very good if you review trigonometry. Especially, it would be good to if you review what is sine, cosine, and tangent of 0, pi over 6, pi over 4, pi over 3, pi over 2, pi, 3 pi over 2, and 2 pi. So these are things that you need to know. It's good to memorize them actually. But if you don't want to memorize them, at least review them. So you would have almost in your mind what these values are. I'm not going to write them now, but you need to feel this table for yourself later. It's good to know them. Now, if we have a vector v, which is not units, not necessarily units, just another vector, any vector. Say, this is the vector v. We know there exists a vector u, unit vector, a vector with length 1, in direction of v. Right? U is something like this. We can measure this angle with the x-axis. Say this angle is theta, right? We just said u is equal to cosine of theta and sine of theta, right? On the other hand, if you remember what I said earlier, the unit vector in direction of v is equal to v divided by its length, right? So if I multiply both sides by the length of v, I would see length of v times u is equal to v. I'm dividing both sides of this, I'm multiplying both sides of this equation by the length of v. Now, look at these two things at the same time. V is equal to length of v times u. But instead of u, I would write this vector here, cosine theta and sine theta. This is quite useful. Let's first solve an example to make sure we are not going to get confused, and then I will tell you what it is good for. Let's say we have a vector v with coordinates 4 and let's use something which makes sense. Something that I know its coordinates. Let's say let's say 2 and 2. It's a vector v with coordinates 2 and 2. 1, 2, 1, 2. This is the vector, right? This is the vector v. First, I would compute u, the unit vector in direction of v. I said u is v divided by its length, right? What is the length of v? I should use Pythagorean theorem. Look at this triangle here. This side is 2, this side is 2, c, the length is unknown. Pythagorean theorem says c squared is 2 squared plus 2 squared, right? 4 plus 4 is 8. So c squared is square root of 8, which is the same as 2 radical 2, right? C is equal to 2 radical 2. Therefore, u, the unit vector in direction of v, is equal to v. What is v? V is 2 and 2 divided by its length, which is 2 radical 2. So the coordinates are 2 over 2 radical 2 and 2 over 2 radical 2. Well, I can cancel this 2 with this 2 and this 2 with this 2. It is equal to 1 over radical 2 and 1 over radical 2. 1 over radical 2 is actually equal to radical 2 over 2. It is a better way of writing this. So that's the unit vector in direction of v, right? Or maybe I can just keep it as, I'm sorry, I can keep it as 1 over radical 2, 1 over radical 2. That's the unit vector in direction of v, right? But on the other hand, u should be cosine theta sine theta. What is theta? Here, cosine of theta equals sine of theta is equal to 1 over radical 2. What is theta? Yes, pi over 4 or 45 degrees, but we prefer to say pi over 4. That is true, pi over 4. So if I look at this vector v, which is 1, 2, and 1 and 2, this angle here is pi over 4. Now I can present v as I said, the length of v times cosine theta sine theta. We computed the length of v. What was it? The length of v was 2 radical 2. This is the length of v. So the length of v is 2 radical 2. And the cosine theta and sine theta are cosine of pi over 4 and sine of pi over 4. So that's another way to present v. Sometimes we prefer to present a vector like this. It might look a little complicated, a little confusing, but actually it has a lot of benefits doing so, yeah. So let's solve another example to make sure we understand what we are doing. Let's say we have a vector v. Let's say the coordinates are, this time, the coordinates are 3, radical 3, and 3. Okay? So if I look at this vector, radical 3 is almost 1.7. So radical 3 is almost 5.1. It's a little above 5. So v is something like this: 1, 2, 3, 4, 5, a little after 5. Then the other coordinate, the other component is 3, so this is v. Okay. Now, the first thing is to compute the unit vector in direction of v. The unit vector in direction of v is v over the length of v. What is the length of v? So again, we should use Pythagorean theorem. This side is 3 radical 3. This side is 3. This side is the unknown c. C squared is equal to 3 radical 3 squared plus 3 squared. 3 radical 3 squared is 9 times 3, which is 27. The other one, 3 squared, is 9. The sum is 36. So c squared is 36, c is 6. So the length of this vector c is actually 6. Now this unit vector is v, 3 radical 3 and 3, divided by 6. Yeah. Therefore, it is 3 radical 3 over 6 and 3 over 6. I continue here. U would be equal to, well, I can simplify it. 3 cancels with the factor of 3 and 6. I would get radical 3 over 2. And 3 over 6 is the same as 1 over 2. Now remember, U is always equal to cosine of theta, sine of theta. It means cosine of theta is equal to radical 3 over 2. Sine of theta is 1 over 2. What is theta? Theta is something which its sine is equal to 1 over 2. It's pi over 6. Therefore, theta is pi over 6. So that's another way. So this angle is pi over 6. That's another way to present vectors. We can find the angle they make with the x-axis, and we have their length. So v is equal to its length, which is 6 times cosine theta, which is the square root of 3 over 2, and sine theta 1 over 2. And yeah. Is there any question here? You might feel you need to solve some more problems to get used to it and remember trigonometry better. But if there's any question, you can ask me now. We have time to go over the details if you're confused. Okay. Okay, if there's no question, let's continue. I would skip the part in this chapter 11, which is about the applications of vectors, finding resultant force and things like that, and finding velocity. I don't care much about that. It's just they're just computations, adding vectors. Why u is equal to sine, cosine theta, sine theta? Good question. So I said when we have a vector u, which the length of u is 1, and makes angle theta, it's equal to the vector u is equal to cosine theta, sine theta. Actually, it's quite simple. So this is the x-axis, right? So if I write u as, it has 2 coordinates. Let's show the first one with A, the second one with B. I want to see what is A, and I want to see what is B, right? So if the first coordinate is A, it means this length is A. The second coordinate is B, it means this length is B, right? But if this length is B, this length is also B here, right? Remember, what is the definition of cosine in a triangle? Here we have, look at this blue triangle. What is definition of cosine? You can unmute yourself and say it if anyone remembers. If you have a triangle, what is sine? What is cosine? Yeah, you're correct, but you should say which one you are saying. Yeah, okay. So if you have a triangle, A, B, C, right? Cosine is actually A over C. And sine is B over C. Yeah, you're all right. That's very good that you remember that. And sine is B over C, right? But what is C here? C is the length of this side. What is C? U is a unit vector. Remember, U is the unit vector. So this is the length of C here is 1. So here we have A, yeah, you're right, over 1. Here we have B over 1. But dividing a by 1 gives us a, dividing b by 1 gives us b. See what we got. Cosine of theta is equal to a. Sine of theta is equal to b. Now, what are a and b? A and b are coordinates of u. U equals a and b, but a is equal to cosine of theta, b is equal to sine of theta. So it just follows from definition of the sine and cosine in a right triangle. Therefore, any unit vector u is equal to cosine of theta and sine of theta, where theta is the angle it makes with the positive direction of x. Yep, you're welcome. Okay. Okay, so let's see what is the next thing we should talk about. Yeah, I try not to be very fast because honestly, this course will get hard, very soon. And I don't want to make things harder. Let me be honest. Actually, when I was undergrad myself, for me, multivariable calculus was the hardest course. I had more problem with multivariable calculus with the advanced math courses I took when I was undergrad. Even I took some grad courses, math grad courses, which I didn't have so much difficulties understanding it. Like higher dimensional spaces and things we would get to, especially the integrals about Stokes theorem, divergence theorem, Green's theorem, they were quite complicated and hard for me. So I want to be as slow as possible so we have enough time to understand the basics quite well and don't just jump into the more complicated part. Okay, so yeah, sure. Yeah, so we talked about two-dimensional case. We talked about planes. Planes are two-dimensional, right? They're two-dimensional spaces. Now, we can think about space. Space is three-dimensional. Right? Just like the world around you, right? It's three-dimensional. So it has three directions. There is the x-axis. There is y-axis. And then there is z-axis. There are three directions. And any point like P, we need three numbers to locate P in this space. So for example, if the coordinates of P are 2, 3, and 1, it means on the x-axis, we should look at the point 2, 0, 1, 2. I'm showing it with the red dot there. That's 2. That's the x-axis. The second component, second coordinate or second component, they have the same meaning, is on the y-axis, and it's 3. 1, 2, 1, 2, 3. I think Blackboard has a little delay. Am I right? When I write, it takes a little time until it shows it to you. Yeah, a little. Okay, maybe I should first write and then say it. Yeah, okay, so we have 1, we have 2, and then we have 3. 1, 2. And then on the z-axis, the last one is the z-axis, the third component, and it's 1. So here we have 1. And these three numbers are supposed to give us the location of P. How? It means the x-axis we have 2. So from the origin, we would start and we come to get to 2. And then y-axis is 3. I would go towards y-axis to right by 3. I would get to this point. You see, it's parallel to y-axis. And then the last coordinate is 1, parallel to z-axis. I would go up by 1. I'm going above the plane. I'm going towards the, maybe I should go a little more to make it more visible. And that's where P is. I can complete this picture by drawing these things. Okay, I didn't do it well. Maybe here. This is P. It's a little bit hard to draw because it's three-dimensional. I would try another time. Okay, let's do another one. Let's say we have a point P equal to -2, let's say +2, -3 and 4. So we have our 3 directions. In the first component is 2. So in direction of x, we look at the point 2. So we have 1, and then we have 2. The second coordinate is -3. So it's in direction of y, but it's towards the negatives. -1, -2, -3. That's here. And the last coordinate, the third one, is in direction of z. It's 4. So 1, 2, 3, 4. Okay, so where is P? The point P is located, when I want to find P, so what I would do is that I would say in direction of x, the coordinate is 2. So I would start from the origin, I would come to this point 2. Then the second coordinate is -3. So I should go in direction of y, but towards negatives by 3. So you would see it's parallel to the y-axis. I would get to this point. And the last coordinate is 4, so I should go up parallel to z by 4. I would get to this point. This is the point P, which its first coordinate is 2, the second coordinate is -3, and the last coordinate is 4. So that's the way to find the coordinates for these points, or find points using the coordinates, okay? And here I have R. The x-axis is a real line. It looks like R. It contains all the real numbers. The y-axis is a real line. I showed with R. The z-axis is a real line. So I have three versions of R. That's why I showed this space with R3. It's a three-dimensional space. I showed with R3. And in order to locate any point, I need 3 numbers, right? That's what we mean by a three-dimensional space. We need 3 numbers to say where each point is, okay? Okay. Okay, now let's for a second go back to the 2-dimensional case. I use Pythagorean theorem to find the length of vectors. I can write down the Pythagorean theorem in a slightly different way. If I have 2 points P and Q, and if I want to see what is the distance between P and Q, well, I can use the Pythagorean theorem. I can connect P to Q, I can make a right triangle and things like that. But there is also another way. So, for example, let's say P is 1 and 1. Say this is 1 and 1, and say Q is 3 and 4. Maybe It really doesn't look good. Let's say P is 1 and 2. Makes more sense, huh? And Q is 3 and 4, right? I want to see what is the distance between P and Q. One way to do it is by defining D to be the distance. It's equal to radical. Okay, look at the first coordinates, 1 and 3. We can subtract them, 3 minus 1 squared. And then we can add the subtraction of the second coordinates, 4 minus 2 squared. Radical all of that. So here 3 minus 1 is 2, 4 minus 2 is 2, 2 squared is 4, 2 squared again is 4, 4 plus 4 is 8, it's square root of 8. That's another way to compute the distance. That's actually the same thing, I'm just writing it slightly different. So just as another example, if P is minus 1 and 3, and Q is 5 and 7, I want to find distance between P and Q. The distance is the square root of, okay, I should subtract the first coordinates, 5 and minus 1. It would be 5 minus 1 squared. And then I should look at the second coordinates. It would be 7 minus 3 squared. Now 5 minus 1 is 5 plus 1, which is 6. 6 squared is 36. 7 minus 3 is 4. 4 squared is 16. Their sum is 52. So the distance between them is radical 52. Okay. That's the way to compute distance between 2 points in 2-dimensional space. Now, how can we find the distance between 2 points in 3-dimensional space? So suppose we have this 3-dimensional space. And we have 2 points. Let's say we have P and we have Q. Okay, so let's say they have some coordinates. Say P is, the X coordinate is 3, the Y coordinate apparently is 0 and 2. The last coordinate is 2. So 1, 2, 3. It doesn't move in Y coordinates, so the second coordinate is 0. The last coordinate is 2. What about Q? Okay, it seems the first coordinate of Q is 0. If we look, Q is here. The first coordinate is 0. The second coordinate is 3. The last coordinate is also 3, right? I'm just saying some numbers and don't matter really. So the distance between P and Q, I would show it with D of P and Q. It means the distance between P and Q. I should kind of compute it the same way as I did for a 2-dimensional case. I should subtract the first coordinates and square it. So it would be 3 minus 0 squared plus. And it also doesn't matter if you subtract the first one from the second one or second one from the first one, you would get the same thing. And then I have 0 and 3, so it would be 0 minus 3 squared. And then I should do the same thing with the last coordinate, 2 minus 3 squared. So 3 minus 0 is 3, 3 squared is 9, plus 0 minus 3 is -3, but when you square it, it's always going to be a positive number. So it's going to be 9 again. And finally, 2 minus 3 is -1, -1 squared is +1. So the sum is going to be 19. So the distance is the square root of 19. So that's the way to compute the distance of 2 points in 3-dimensional space. Maybe I would just do one more example. So if P in the 3D, okay, just to get a feeling of, say, 4-dimensional space. If P is a point, let's say P is a point in a 4-dimensional space, then you would expect to express P using 4 numbers, right? So P, the coordinates of P should be something like this: 2, 3, -1, 3. Okay, someone is asking, what is the difference between length of a vector and distance between 2 points? Actually, there's no difference. So length of a vector is actually the distance between its initial and final points. So the question is that what's the difference between length of a vector? You have a vector, it has a length. What is the difference between length of a vector and distance between these 2 points P and Q? They are the same. Distance between P and Q is equal to the length of this vector connecting them. They are the same. We are just using, say, 2 different words, but they're actually the same. Thank you. Yeah, I was using Pythagorean theorem, but what I wrote earlier is also Pythagorean theorem. So things I have here, the way okay, I'm sorry, maybe I was a little fast. The way I computed the distance between 2 points this way is actually the same as Pythagorean theorem. It's just slightly writing it in different way. So it might look a little different to us, but actually it's just another way of writing Pythagorean theorem. You are completely right. Oh, I didn't write oh, okay. I didn't fill in. I said you should. Actually, I'm writing some notes for you. I have the table in the notes. I will upload the notes of the class after the class in Blackboard. You don't need to take picture. Okay, so yes, so length of a vector is the same as distance of 2 points. And we use 2 different ways, but both of them in reality are the same. Both of them are just Pythagorean theorem. Okay, so if I have a point, I can't imagine 4-dimensional space, but let's for a second say, what if there is a 4-dimensional space? If there is a 4-dimensional space, any point in that space should be presented with 4 numbers rather than 3 numbers, right? The coordinates, there are 4 numbers. I need 4 numbers. So if Q is another number, there should be something like 1, 0, I don't know, 2, 5. These points should be the coordinates in 4-dimensional space, right? And if they ask me, what is the distance between P and Q? Although I cannot see this 4-dimensional space, I can use the same method, which I told you is actually Pythagorean theorem, although we are writing it in a slightly different way. We can, using the same way, we can compute the distance between P and Q. We can look at the first coordinates, we can subtract them and square. We can look at the second coordinates, we can subtract them and square. We can look at the third coordinates, we can subtract them and square. And we can look at the fourth coordinates, and we can subtract them and square. So 2 minus 1 is 1, 1 squared is 1, 3 minus is 3, 3 squared is 9. Minus 1 minus 2 is minus 3. Minus 3 squared is plus 9. Remember, square root of a number is always a positive number. 3 minus 5 equals minus 2. Minus 2 squared is plus 4. Okay, what is the sum? 23, huh? The distance between them is the square root of 23. So we can compute the distance between 2 points in 4-dimensional space. Can we compute the distance between 2 points in the 5-dimensional space? Yes. Let's just say we have a point in 5-dimensional space. If it's something in 5-dimensional space, the point should have 5 coordinates. We need 5 numbers to locate the point. So the point should be something like 1, minus 1, 0, 3, 2. See, 1, 2, 3, 4, 5. We need 5 numbers to locate a point inside 5-dimensional space. Another point can be something like this. And then if they see, we need 5 numbers. And if they ask us, what is the distance between P and Q? We would do the same thing. We say 1 minus minus 2 squared, first coordinates. Minus 1 minus 3 squared, second coordinates. 0 minus 2 squared, third coordinates. 3 minus 2 squared, fourth coordinates. Plus 2 minus 1 squared, fifth coordinate. And we add all of these things. 1 minus minus 2 is 3. 3 squared is 9. Minus 3 minus 1 minus 4 squared is 16. Plus 4 plus 1 plus 1. If we add all these numbers, we would get 1 plus 9 is 10. 1 plus 4 is 5. It's 15. It's 31. It's the square root of 31. So actually using this theorem, which is, I told you, it's just another version of Pythagorean theorem, we can compute the distances in any dimension, even if we can't really see those dimensions. We can compute the distance between 2 points in any dimension. Okay, any question here? Is everything okay? Okay, that's good. Okay, so let's see. Okay, we have, I guess, 1 more hour. Yeah. Okay, let's continue with what do I want to talk about now? Okay. Now, again, let's go back to plane into 2-dimensional space with coordinates x and y. I think we have a high school student, right? Even if you're, I mean, don't be ashamed to ask questions. Yeah, good. Yeah, okay, you are asking questions. Oh, both of you. That's very good. That's very good. That's amazing, actually. Yeah, don't be afraid to ask questions. I mean, it's perfectly fine. It's actually, I really like to hear more questions. Okay, let's go back to 2-dimensional space. We can have, we have some geometric objects. One of the very interesting geometric objects is a circle, right? Yeah, me too, actually. I really wanted to take some good courses when I was in high school. The technology wasn't there, and also there was no quarantine, so it wasn't common for people to take so many online courses. No, well, at least when I was in high school. Okay, so let's look at the circle. Actually, we can describe these objects using, using equations. So any geometric object, here we have circles, different sizes, different locations, different radius. We can describe them using an equation. How? There are two things which kind of characterize the circle for us. So if you have a circle, there are two important properties. Can anyone guess what are those properties which they tell us everything about the circle? Yeah, one of them is radius, and that's the important one actually. And the other one is the center, exactly. So if I know the center of the circle, say center is here. This is the center. And if I know the radius, r, I can draw the circle, right? That would be the circle. Now, there is an algebraic equation describes this circle. So let me write it here. So let's take the center to be the origin. Let's take the center to be 0 and 0 in the plane. It's the origin, it's this point. We usually show it with O. It stands both for origin and it also stands for 0. And it's the center of our circle. And let's say the radius is 1. Radius is a positive number. So the circle would look like something like this, and the radius is 1. The equation of this circle is x squared plus y squared equals 1. What does this mean? It means any point you take on this circle, any point, say this point here, P. If you look at the x-axis, you would get a number here, x. If you look at the y-axis, you would get a number here, y. If you square this point, this number x, and if you square this number y, and if you add them, you would get 1. That holds for all the points on the circle. And any point with this property is on the circle. So this is the equation describing the circle with center 0, 0, and with radius 1. So for example, let's look at something here. Let's look at this circle again. This point is actually a point on the circle with coordinates square root of 2 over 2 and square root of 2 over 2. This is a point on the circle with radius 1. We can check that. We can check if we square x and y and add them, we would get 1 or not. Here you should trust me. This is indeed a point on the circle. If you look at this point, square root of 2 over 2 and radical 2 over 2, but for x and y, we would end up with a point, say P. This is on the circle, and x squared would be square root of 2 over 2 squared. Square root of 2 squared is 2. 2 squared is 4. 2 over 4 is the same as 1 over 2. Y squared is the same thing. Radical 2 over 2 squared, which is 2 over 4, which is 1 over 2. If I add them, if I add x squared to y squared, I would get 1 over 2 plus 1 over 2. It would be 1. That holds for any point on the circle. Let's look at another point on the circle. Let's take Q here. another point on this circle with radius 1, with coordinates 1 over 2 and square root of 3 over 2. This is another point on this circle. Here, x is 1 over 2, y is square root of 3 over 2. X squared is 1 over 4. Y squared is radical 3 squared, which is 3. 2 squared is 4. Now, x squared plus y squared, sorry, this is 4, would be 1 over 4 plus 3 over 4. It's 4 over 4, which is 1. So for any random point you choose on this circle, if you look at x and if you look at y, the coordinates of that point, if you square them and if you add them, you would get 1. That's what we mean by this equation describes this geometric object. And that's a very important thing in mathematics. That's maybe one of the most important things in mathematics. When you have a geometric object, you can either kind of think about it intuitively, like a circle. You can think about the circle. Circle has a shape, we know it, we know how it looks like. Or you can think about it algebraically, using equations. So you can think about circle with center equal to the origin and radius 1, or you can say x squared plus y squared equals 1. They are exactly equivalent. Some people are better at thinking more intuitively and more geometrically. Some people are better thinking using the algebraic equations. So this is a circle. This is also a circle. Although we can't see, if you look at this equation, actually you can imagine the circle in your mind, right? Okay, let's look at slightly more general case. If we have a circle with center C, say C is A and B, it's just a point, A, B. That's the point C, which is the center, and with radius R, we would end up with a circle. The equation of this circle would be x minus a squared plus y minus b squared equals r squared. That would be the equation describing this circle. So for example, what is the equation? Find the equation of the circle with center C equals, say, 2 and 3, with radius equal to 3. What is the equation? Using this formula here, you would say the equation is x minus 2, the first coordinate, squared plus y minus 3, the second coordinate, square, equals r squared, the radius. Radius is 3, 3 squared is 9. That would be the equation of this circle. So in this way, we can write down the equation of any circle in plane. Okay. Any question here? Also, if you are missing some parts of the class because it's online, I know. I mean, I had online classes through my PhD, and at some points I left, I went to the other room, I came back, I missed something. And you know, math has this property that if you don't understand some part, it might be very hard to continue. So if you are not listening to all of the class, I recommend you later to look at the video and try to kind of fill in gaps and watch the places you missed, right, before the next class, because If you miss something now, Thursday it's going to be, it becomes harder to continue. If you don't understand the topic on Thursday, it would be harder to continue on next Tuesday. So try to watch the videos. And also you can, as I said, I have office hours. We can have Skype or Zoom meeting and you can ask me the questions. Okay, so we have circles in plane, which looks like this. If we go one dimension higher to space, rather than circle, we would have sphere. So we have spheres in space. The spheres look like this. I'm not sure if it's like a ball or earth. And it's the surface of that object, not inside. Just like here, by the circle, we don't mean things inside. We just mean the boundary of the circle, just this one-dimensional curve. That's what we mean by a circle, not the things inside. Also here about the sphere, we don't mean the things inside. We just mean the surface of Earth or surface of the sphere. So the surface is something two-dimensional, right? We're just thinking about the surface. Okay, so what is the equation of the sphere in space? It's very similar. So if the equation of circle with center C equal to say A and B and radius R, if the equation of that is x minus a squared plus y minus b squared equals r squared, we kind of can look at this equation and guess what is the equation of a sphere in three-dimensional space. So in three-dimensional space, in order to write down equation of a sphere, again, in three-dimensional space, we need a center of the sphere, and we need again a radius. And using that, we can draw sphere. It's a sphere. It's kind of area of a ball around that point. It's a two-dimensional thing now. So if this center now, it needs three numbers as its coordinates, say A, B, C. It's something in three-dimensional space, so it needs three numbers. And radius R is just a real number, positive number. The equation of a sphere with center ABC, well, maybe I shouldn't use ABC because I already have C. Let's use other letters. What letters should I use? Let's say E, F, G. They're just numbers. The equation would be x minus e squared plus y minus f squared. Up to this point, it really looks like a circle. It has another part, which is z minus that last number squared equals r squared. Let's look at an example. Let's look at an example to understand what's going on. So, for example, consider the sphere with center C equal to 1, 2, 3. So where is that? X is 1, Y is 2, and the last component Z is 3. So where is C? I should come here. I should go right parallel to Y, and then I should go up by 3. I would get to this point. That's C. With radius, say 2. So the radius is 2. I can consider a sphere around C with radius 2. What is the equation of that? So find the equation. Find the equation. That would be the question. Find the equation of sphere with center 1, 2, 3 and radius 2. What is the equation? The equation is x minus the first coordinate, 1 squared, plus y minus the second coordinate, 2 squared, plus z minus the third coordinate, 3 squared, equals the radius squared, 2 squared, which is 4. Okay, does it make sense? Is there any question on how we should write the equation of a circle and sphere? Oh, how does the equation of a circle? Okay, so let's go back. So where does the equation of circle come from? This is a circle. For simplicity's sake, the center is 0 and 0 and the radius is 1, right? The other circles are similar. I want to find the equation of this circle, right? Yeah, David, I will come back to your question. Yeah, you're perfectly right. So I want to find the equation of this circle. I should choose a point. What does the equation mean? It means if you choose any point P on this circle, it has 2 coordinates, x and y. The equation means what is the relation, what is the formula which governs x and y. That's the meaning of the equation, right? Now here we have a unit sphere, right? The r is equal to 1. The radius is equal to 1, right? Look at the vector which connects the origin to P, PO, this vector. It's, as we said earlier, it's P minus O. P is x and y. O, origin is 0 and 0. So the coordinates of this vector are also x and y, right? Also, it is a unit vector. Do you agree? This PO, this vector which connects the origin to P, is a unit vector because the circle has radius 1. Yeah. So this is a unit vector. Oh yeah, thank you. It's PO is yeah, I made a mistake here. Sorry. Well, no, PO, by PO I mean this. Okay, yeah, I changed notation in the middle. It's OP. You're right. It goes from O to P, so it's P minus O. Thank you. So yeah, so this is also a unit vector. Remember, any unit vector, well, for example, this OP is an example of, if I look at this angle, if it's theta, any unit vector has, I can write it as cosine of theta and sine of theta, right? Do you agree? Because OP is a unit vector. Any unit vector can be written as cosine theta and sine theta. It means x is cosine theta, y is sine theta. What is the equation which governs cosine and sine? What is the relation between sine and cosine? The important thing we know is that sine squared plus cosine squared equals 1. But because sine is equal to y, cosine is equal to x, it means x squared plus y squared equals 1. You don't need to know this thing here. This is a proof. You don't need it. That's just an answer to a question. Okay. Okay, let's continue. Yep, you're welcome. So equation of a circle, let's sum up. Equation of a circle with center C equals to, say, A and B with radius R is x minus a squared plus y minus b squared equals r squared. If you go one dimension higher, we get to sphere. It has, the center needs 3 numbers because sphere is something in space. The center needs 3 numbers, a, b, c, and then radius r. The equation is x minus a squared plus y minus b squared plus z minus c squared equals r squared. That's an equation of sphere in 3-dimensional space. Now, circles, you know, we can go 1 dimension higher. We can go 1 dimension higher, and that's interesting. Let's do that. Let's go just 1 dimension higher. So we have circle inside R2. We have sphere inside 3-dimensional space, which we showed with R3. Let's consider 4-dimensional space. Okay. In order to present 4-dimensional space, I use the notation R4. It just means 4-dimensional space. So by that, I just mean a 4-dimensional space. What is the, if circle goes to sphere, what should be the next thing? What is the next thing? What is the, if we suppose sphere is a higher dimensional version of a circle, if we go 1 level further, what do we get? Yeah, the name is HyperSphere. You can think about it as moving sphere, but I would comment on that later. Let's name it HyperSphere. What you're saying in some sense is correct. It's just a name. People call it HyperSphere. So we can see circle, we can see sphere, we can't see HyperSphere, but we can write down the equation for the circle. That's the equation for circle, right? It's the equation of circle. We can write down the equation of sphere. So what is the equation for HyperSphere? If I show the the coordinates on R4, if I show them with x-axis, I would have in 4-dimensional space, I would have x-axis, I would have y-axis, I would have z-axis, I would have 1 extra axis. Let's name it t-axis. I need 4 axes. If I want to locate points in 4-dimensional space, I need 4 axes, because in R2, I have 2 axes in 2-dimensional space. In 3-dimensional space, I have 3 axes. So in 4-dimensional space, I need 4 axes. Let's just name it T. It's not hard to guess what is the equation of HyperSphere. It would be x minus, so let's say the center is a point, A, B, C, D. You know, because the center is a point in 4-dimensional space, the coordinates need 4 numbers. We need 4 numbers to locate the point in 4-dimensional space. And the equation would be x minus a squared plus y minus b squared plus c minus, plus z minus c squared. And then we have extra thing, t minus d squared equals the radius squared. So this would be the equation of a HyperSphere, equation of HyperSphere in 4-dimensional space. Does that make sense? Any question here? Yeah. So it's interesting. Although the circle is inside R2, I'm just speaking now, these things are not really part of the course. Although, well, I'm talking about that. Circle is something in two-dimensional space, right? But what is the dimension of the circle itself? Remember, by the circle, I just mean the boundary of this shape, not what is inside. What is the dimension of the circle itself? Well, the circle is one-dimensional. The circle itself, because it looks like a curve, right? It looks like a line. It just has some length. So the circle itself is one-dimensional. So circle is a one-dimensional inside a two-dimensional space. What about sphere? Sphere, I mean just the surface of a sphere. What is the dimension of a sphere? Yeah, that is true. The sphere itself, its surface is two-dimensional inside a three-dimensional thing. So R4 is a four-dimensional space. So you can guess hypersurface itself is something, yeah, that is true. Three-dimensional inside four-dimensional. Okay, but we don't need to pursue that anymore. Okay, let's see. Okay, let's just try. You know, you don't need to think about these things if they come in your if they will be in the exam or not. Don't think about the grade. I promise you would get a good grade if you just try to learn something. The grade really doesn't matter. Okay. Okay, let me tell you one more simple thing. One is that inside three-dimensional space, what is a hypersphere? Okay, what does, you know, that's quite interesting. So now you're asking, what is a hypersphere, right? What is? But what does it mean? What is the meaning of this sentence? You know, what does it mean to ask what is something? When you are doing math, the answer, one answer to what is question is giving the equation. It's what that this equation describes, even if you can't see that, you know? So maybe for a mathematician, a circle is the same as x minus a squared plus y minus b squared equals r squared. So if you ask a mathematician what is a sphere, what is a circle, they might give you different answers, but definitely one answer would be just writing down this equation. That's the answer to what is a circle for a mathematician. Now about a hypersphere, which is something inside four-dimensional space, one answer would be hypersphere is the thing that this equation, which I showed you, describes this equation, even if we can't see it. Okay, this is not part of the course, okay? This four-dimensional thing is not in the course, but just it's nice to see that. So this is equation of a circle. This is equation of sphere. We can't see circle and we can't see sphere. We can't see hypersphere, but we still have the equation. And we can say hypersphere is what this equation describes. Okay, does that make you happy or? Yeah, we might be able to give more other characteristic of these things later. But at this point, we would say hypersphere is what this equation describes. I know it might be a little confusing. I hope it doesn't kind of frighten you. It's not part of the exam or anything like that.
It's just that I was wondering, you said that the fourth dimension, at the beginning you said that the fourth dimension could be time, but we can't see it.
Yeah.
And
So
that's why
yeah,
I said
you're right.
moving sphere, because I thought that
Yeah,
it's
yeah,
okay.
yeah, yeah. Yeah, I got that. And that was interesting. But you see, we can have 4-dimension as 3-dimension space plus 1-dimension time, or we can have 4-dimension as all of them are space. You know, and this hypersphere is inside a 4-dimensional space. All of these 4 dimensions are space. You know, what I wanted to say is that we can have any dimension. You can just assume we have a 10-dimensional space. And you can ask, what is the hypersphere of this 10-dimensional space? And you can just write almost the same equation and just add more, you know, variables. But you are right. In the hypersphere I mentioned is inside the 4-dimensional space, which all of those dimensions are spatial dimensions. It's like, forget about time. It's like we are living a 3-dimensional space, but there exists another spatial dimension that which we can't see. And this is the equation of this hypersphere in that space. Okay, anyway, let's not get too deep into these, because we would later come back and we would understand them better. Let's go back to basics. Okay, so, okay, I hope that the answer was good enough. Let's go back to R3. We have x-axis, we have y-axis, and we have z-axis, right? And any point P can be presented with 3 numbers. Let's say 2, 3, and -2, right? It's a point. Now, remember in R2, when we were working with R2, I said we can look at the unit vectors, which one of them is equal to 1 and 0, the other one is equal to 0 and 1. We showed 1, 0 with I, we showed 0, 1 with J, right? These are the standard, we call them standard unit vectors in R2. We have standard unit vectors in R3 too. We have this vector, which is 1, 0, 0. We have this vector, which is 0, 1, 0. And we have this vector, which is 0, 0, 1. Okay, so this vector, the coordinates of this vector is 1, 0, 0, the first one. The vector on the y-axis, the coordinates are 0, 1, 0, and the coordinate on z-axis is 0, 0, 1. We show the first one, 1, 0, 0. We still show it with I. The second one, 0, 1, 0, we show it with J. And the last one, 0, 0, 1, we show it with K. Just like the 2-dimensional case, we can use these notations to present any vector. So for example, let's say we have a vector, oh, I use that. Let's show it with V. Let's say it's a vector. We have a vector 2, 3, -2. I can write 2, 3, -2 as 2, 0, 0 plus 0, 3, 0 plus 0, 0 -2. Why can I do that? Because when we add vectors, we do it component-wise. So when I'm adding these 3 vectors together, I would add the first component to the first component to the first component. So I would get 2 plus 0 plus 0, which is 2. And then I would add the second component to the second component to the second component, which is 0 plus 3 plus 0, which is 3. And then I would add the third component to the third component to the third component, which is 0 plus 0 -2, which is -2, right? So I can do that. And then 2, 0, 0 is equal to 2 times 1, 0, 0. Why? Because I do the multiplication component-wise. I should first multiply 2 by 1, which I would get 2, then 2 by 0, which would be 0, then 2 by 0, which would be 0, plus 0, 3, 0. That is equal to 3, 0, 1, 0. If I do this multiplication, I would multiply 3 by 0, would give me 0. I would multiply 3 by 1, would give me 3. And I would multiply 3 by 0, which would give me it. And finally, minus 2 times 0, 0, 1. Same thing. Now, this first thing, 1, 0, 0, I said we showed with I. The second one, 0, 1, 0, I said we showed with J. And the last one, 0, 0, 1, we showed with K, right? So this thing is equal to 2I plus 3J minus 2 minus 2K. So I can write down this vector 2, 3 minus 2 as 2I plus 3J minus 2K. That's another way of writing vectors in three-dimensional space. And well, this is very similar to the thing we saw before. If I have a vector V in three-dimensional space, it would have 3 coordinates, x, y, z. The length of this vector V is defined to be the square root of x squared plus y squared plus z squared. So that's completely similar to the two-dimensional case. It is again Pythagorean theorem. And it is again equal. The length of a vector in three-dimensional space, again, is if it connects P to Q. The length is again the distance between P and Q. So if you have a vector V, which the coordinates are 2, 3, and 1, the length of V is equal to square root of 2 squared plus 3 squared plus 1 squared, which here is 4 plus 9 plus 1, which is the square root of 14. Any question here? Also, if we have two vectors in three-dimensional space, we can add them. So if we have 1, 3, 0, and if we have another vector in three-dimensional space, 2, minus 1, 4, we can add them. V plus U means we can add them component by component. 1 plus 2 is 3. 3 plus minus 1 is 2. 0 plus 4 is 4. Just similar to the two-dimensional case, if I have a vector, I can multiply it with a number. It would be 2 times V if V is 1, 3, 0 here. 2 times V means 2 times 1, which is 2. 2 times 3, which is 6. 2 times 0, which is 0. And it has the same geometric meaning. If it's V, 2 times V means same direction. The size is 2 times V. And what is minus V? Again, it means in the opposite direction with the same size. So for example, if this is U, what is minus 2U? It means in the opposite direction, but the size should be 2 times of that. Maybe I should make you a little shorter. Something like that. Okay, does that make sense?
I have a question about the unit vector in 3D space.
Yeah, okay. Yeah, we can do the same thing. Okay, let me do that too. So if we have a vector V in 3 space, sometimes I say 3 space. 3 space just means three-dimensional space. Let's say the vector is 2, 3, and 4. They might ask us find the unit vector in direction of V. It means look at the three-dimensional space, look at the vector V, say it's something like this. The unit vector in direction of V, it means it's in the same direction, but its length is 1. And the formula for finding U is the same thing. Divide U by its length.
I'm
so
more
what is,
about
yep.
if we can use the cosine sine, and would tangent be represented to make up the 3 angles for
It's not the
3D
tangent.
space?
We would get to that. It's not tangent. We need actually 2 angles. 1 angle is not enough anymore. We would get that. It is called spherical coordinates. Yeah, I will talk about that probably on Thursday, I guess. Yep.
Okay,
So
thank you.
Yeah, you're welcome. So let's continue this thing, and then I would explain what you asked in future. So what is the length of V? The length of V is square root of the first coordinate squared, the second coordinate squared, plus the last coordinate squared. It is equal to 4 plus 9 plus 16. Yeah, I would explain that in a second, okay? So 4 plus 9 plus 16, okay, what is the sum? 25, 29, square root of 29. So the length of V is the square root radical 29, right? And what is V? V is 2, 3, 4. So we should divide that by radical 29. We should divide each number by that. So it would be 2 over radical 29, 3 over radical 29, and 4 over radical 29. This is the unit vector u in direction of V. Okay, what the question was, maybe I don't want to mention that now, but just I would mention that this is something we would talk later. He said, if we have a vector v, we can unit vector, say a unit vector u. I said if this angle is theta, u is cosine theta, sine theta. The question was if we can do something similar in three-dimensional space. If we have a unit vector, can we use three numbers to present this unit vector in terms of sine and cosine? I said we need two angles. We need the angle here, and then we need another angle, which is here, which I wouldn't get into now. So it's slightly more complicated. So let's keep that for future. Okay. Okay, any question up to this point? You can just for a few, maybe for a minute, you can just review things I said. If you take notes, you can take a look at your note to see if there's anything you want to ask me now. Can I give a summary about today's topic? I would give you a summary, but on Thursday, not today. You are going to have homework for the next Thursday. I would upload the homework, and I would upload a note as summary. Yeah. I would summarize things which I said today on Thursday because I just told them now. So it doesn't really make sense to summarize them now, but I would tell you a summary on Thursday. Now I want you to, okay, I would stop recording now.